This video is for section 7.3, the sampling distribution of sample means, and it starts off with a problem that we've seen a type of before. Here we're given information about Army helmets, we're given their mean and their standard deviation, and I'd like the probability that a randomly selected soldier's head will have a circumference greater than 23.5 inches. So this is the type of problem we've done before when we talked about normal distributions. We're given information about the head size of soldiers. I'd like to find the probability that X is greater than 23.5, and I drew a nice normal curve here. This is nothing different, nothing new than what we did when we talked about normal distributions. And we could just use norm CDF in our calculator in order to do this problem. But now we have a second problem. Let's take a look at this one here. Now we want what the probability that a random sample of 5 soldiers will have an average head circumference that is greater than 23.5 inches. So notice what's different here. We're not talking about an individual soldier anymore. We're talking about a group of 5 soldiers. And I'd like to know how those groups behave. So if I took 5 soldiers and averaged together their head circumferences, what's the probability that it comes out as greater than 23.5? So here I need to know about the distribution of X bar. So just like any distribution, I need to know the center, shape, and spread of the sampling distribution of X bar in order to be able to do this problem. So first, we're going to start off by taking a look at the shape. So we have our little flow chart here. So let's think about the population. We're told about the population of head circumferences. We are told that they are approximately normal. And those are our X's. Okay? We could take different random samples of size n. Here they're going to be size 5. Perhaps my first sample has 3 soldiers that have small heads, one with a large, one in the middle. Perhaps I could take another sample. Next time I get 5 soldiers whose head circumference tend to cluster around the middle. Maybe in a different sample, I get many large circumferences and one smaller one. But they're all samples of size 5, and I'm interested in the mean of each of these. What would happen if I took these means repeatedly and plotted them? Well, now we're talking about the sampling distribution. The sampling distribution will be approximately normal. Oops. And what's important to note here is the sampling distribution, X bar here, will have a slightly different distribution than a parent population. Because think about it. When we take these samples, no matter how I take them, the average of these will tend to cluster around the center. If I took the average of all of these, it's likely that I will get something towards the center here. So the sampling distribution will have many things in common with the population distribution, but the one thing that'll be different is the variability. So now let's take a look at, and we're going to explore this in class, so you might want to watch this one a few times and pay attention to the ideas that we do in class here. We also need to talk about the center and the spread. Well, the center, if we know that X bar is an unbiased estimator of mu, then we can assume that the mu of X bar will be the mean of the population. Yes, I'm recording in school today, so there are the bells. So this is an important fact here, that the mean of the sampling distribution will reveal the mean of the population. They'll be the same. Well, how about the spread? Now the spread, the mean of X bar, we have a formula for that, and we're going to explore this formula in class, but it's the standard deviation of the population divided by the square root of n. The sample size you take has a pretty big bearing on the standard deviation of the sampling distribution. And it's important to note that we can use this formula if we take a random sample from a large population. That will mean that we have independence here. And again, we can use this formula if we need to, that the population size, as a rule of thumb, should be greater than 10 times the sample size. So we have 2 main formulas here that are pretty easy to remember, and we're going to use repeatedly throughout this section. So right now we have just about everything we need to do this problem. We're told information about the population. We're given the mean and the standard deviation, and the fact that's approximately normal. I want the probability that a mean of 5 comes out as greater than 23.5. I know that the mean of the sampling distribution will be 22.8. This number is the same as the mean of the population. I can find the standard deviation. Whoops, wrote over myself there. I can find the standard deviation of X bar. That's 1.1 over the square root of 5. That'll come out as 0.492. So now I have everything I need in order to do this problem. This means I know that X bar will have a normal distribution, 22.8, 0.492. And now I can just use norm CDF on my calculator in order to find this probability. This problem really takes advantage of a lot of different things that we learn in AP Stat, and we're going to put them all together, and we'll do a lot of problems of this type, but it is important to kind of know the progression of what's happening as we go through the problem. Okay, here's a second situation. This is a couple pages later in your packet. This one's about hot dogs. So if you take a minute and look at this one, we're told about hot dogs. We're given the mean and the standard deviation of individual hot dogs. And now we're going to take a sample of 36 hot dogs. I want the probability that at least that their mean fat content will be at least 18.4 grams. So what's different about this problem? Sample size of 36. I want the probability that a sample of 36 hot dogs has a mean that's greater than 18.4. What I don't know here is I don't know how individual hot dogs are distributed. I don't know if they have an approximately normal distribution. And I can't safely assume that. I'm really not sure. It could be a uniform distribution. It could be skewed. It could be bimodal. I'm not quite sure here. So for this problem, we're going to use a very important theorem in AP statistics. And it says that if the population has any distribution, normal or not, we can employ the central limit theorem. And the rule says that if n is large, and as a rule of thumb, we'll say if n is greater than 30, then the sample mean has an approximately normal distribution. This is a very big rule, and in my class I like to say that if something is a really big rule that we need to understand and absorb, we put a lot of stars around it. This is a big rule, because this lets us say that if we have any distribution whatsoever, we don't need to rely on the population being approximately normal. No matter what happens, we'll be allowed to assume that the sampling distribution is approximately normal if we take samples that are big enough. Now, we'll look at some applets and do some activities in class that will prove this and show that this is true. But for now, we're just going to take a look at it. The central limit theorem, big, big deal. And very big that we understand when it's okay to use it. So let's take a look at what we have. Now, we also going to take a look at our progression again. So our population could have any distribution, any shape. I could have a normal one, a skewed one, bimodal. I'm not quite sure the population is. Maybe I don't know anything about it at all. And I could take samples from it. I can make a box and whisker out of these samples, as long as they are greater than 30, as long as we take samples that have large sample sizes. And if I take the means from these, and I think about the sampling distribution, it's safe to say that the sampling distribution will be approximately normal. This is a very powerful tool, because we know a whole lot of stuff about normal distributions. So in this problem, let's put it all together. We'll still have a mean. The mean of the sampling distribution will be mu. The standard deviation will still be sigma over root n, and the same rules here will apply. We want a large population, we want independence, and we will take large samples that are greater than 30 here. The CLT here is a very powerful rule, because now I can do this problem without even knowing how hot dogs are distributed. So let's put it all together. So we know that x equals the number of grams of fat in our hot dogs. I know the mean of individual hot dogs is 18. The standard deviation for individual hot dogs is 1. But I'd like to know the probability that a batch of 36 hot dogs will have a mean fat content greater than 18.4. Let's see what I can put together here. I need the center, the shape, and the spread. I know that the mean of the sampling distribution will be 18. It'll be the same as the mean of the population. I know that the standard deviation of the sampling distribution will be 1 over root 36. That's 1/6. That's 0.167. And the shape is very important here. Because n is greater than 30, it's 36, we can safely apply the central limit theorem. This right here, let's make sure we're clear on this. This says the central limit theorem, CLT. It is a standard abbreviation that we can use when dealing with sample means. This allows us to say that x bar will have an approximately normal distribution. We have the mean and the standard deviation. And now I can compute this problem just like any other normal distribution problem. And I'm all set to go. I would advise you to look this video over a couple times. We're going to have a couple examples in class that we'll look at. We'll throw some other videos at you. This is definitely one you'll want to repeat and do a couple times and let it sink in. This is not an easy concept to get the first time around. Look at this video a couple times. Look at the resources we give you. And we'll do well on this one together. This is a key concept in AP statistics.